Assalamualaikum and greetings everyone. Today's topic is on line integrals in a vector fields. A line integral of a vector field f on curve C gives the value of work needed to move the object from initial point A to destination point B moving on the given curve C. So f here is considered as force. You're going to move an object from point A, point B that lies on curve C. So line integral in the vector field represent work. Alright, now let's look at line integral on the xy plane. Okay, so if you have a force F given as pxyi plus qxyj, as you can see here, this is a vector field on a 2D. And you're given a curve C given by r equals xi plus yj. Again, this is given in general form, in vector valued function form. Then work done is given by the following notation. So work is equal to integration over curve C, and the integrand is f dot dr. So here you have vector field f dot with vector dr. So vector dr is just you integrate your curve here. So if r is xi plus yj, this is given in general form. So dr is equal to dxi plus dyj. So when you dot vector field f with dr, you get a scalar. So a vector dot with a vector, you get x component multiplied with the x component. So you have pxy dx plus y component multiplied with the y component. Here you have qxy dy. So work is f dot dr, but when you simplify this, what you get is a line integral in a scalar field. You don't have I and j anymore. So work is equal to pxy dx plus qxy dy. So this is line integral of a vector field on a plane. Okay, now let's look at line integral of a vector field in xyz space. Okay, so again, do note that work is equal to f dot dr. So if you have a curve in xyz space and a vector field f in 3D, so now instead of two terms, you have three terms. Work is still f dot dr, but now when you evaluate f dot dr, f is a vector, dr is also a vector. So now your dr has three components, where the x component is just the derivative of the x component of r. So you have dxi plus dyj plus dzk. So when you dot f and dr, you get a line integral of a scalar because you multiply the x component p with the x component of dr, which is dx. So you have this term. And then plus y component of f multiplied with the y component of dr, you get the second term. And then the z component of f multiplied with the z component of dr, then you get this term. So f dot dr, for line integral in xyz space, you have three terms, 1, 2, 3. And again, it represents work done to move an object using force F over curve C from point A to point B. Okay, now let's look at how to evaluate this work. Now, I'm going to start with evaluating line integral on a plane. Okay. So how do we evaluate line integral on the xy plane? Okay, after you perform the dot product, you end up with this pxy dx plus qxy dy. Then two situations must be considered. First is the initial points and the destination points. Whether your initial point and destination point is given as a Cartesian coordinate x0, y0, xn, yn, or are they given as a parameter where point A is at t equals t0 and point B is at t equals tn, because different situations need different evaluation, different kind of evaluation. Okay, and the second thing that you need to consider is how the curve is given. Is the curve given as y as a function of x, or is it given as x as a function of y, or is it given as parametric equation or as vector valued function? Okay, now let's look at how to evaluate in all these situations. Okay, let's look at first case. First case is where your curve C is given as y as a function of x. So if your curve is given as y as a function of x, then from here you get dy dx is equal to f prime x. Then your work, which is f dot dr, when you simplify it, get pxy dx plus qxy dy. And to evaluate this, if your curve is given as y as a function of x, what you need to do is you need to change everything in terms of x. So here we have pxy, so that y there must be replaced by f of x. And here we have qxy, this y also must be replaced by f of x. Dx remain as it is, but dy must be replaced in terms of dx. So dy here must be replaced by dy dx. Okay, then everything would be in terms of x. All right, so this is just so dy must be replaced by f prime x dx. All right, so this is really f prime x dx. So everything now will be in terms of x. And then the limits. How about the limits? So when your integration is with respect to x, the upper limit for x is the x coordinate of the destination point. So in this case, xn. And the lower limit for x is the x coordinate of the initial point, in this case, x naught. And then you evaluate by integrating with respect to x. Now let's look at the second situation. The second situation is when your curve C is given as x as a function of y. So if your curve C is given as x as a function of y, then when you differentiate this with respect to y, you have dx dy is h prime y. Now what you need to do is you need to change all the variables in the integrals to become y. So here we have f dot dr simplified, so we have pxy dx plus qxy dy. Now you have to change all the x to become y. So the first term we have pxy dx, so this x here must be replaced by h of y, and dx here must be replaced in terms of dy. So here dx is going to be equal to h prime y dy. So this is really h prime y dy. And then same thing with q of xy dy. So this x here must be replaced by h of y. Y and dy remains as it is. So now you have an integration where you need to integrate with respect to y. Now the limits. The limits that you need to use would be the y coordinate of the initial point, that would be the lower limit for y, and the upper limit for y would be the y coordinate of the destination point, in this case yn. Okay, so you have two cases. Now let's look at the third case. For the third case is where your curve C is given as vector valued function. So you have x component, y component, or it can also be considered as a parametric equation. So you have x is equal to xt, y equals yt. So now what you need to do is you need to change everything in terms of t. So dx here, so we have pxy dx plus qxy dy. All the x, all the y, dx and also dy must be changed in terms of t. So here pxy dx will become, replace x here with the parametric equation of x, so in this case xt, or you can use this one, it's the same, xt. And y must be replaced by the parametric equation for y, or you can use the y component, it's the same thing. And same thing for qxy, must change that in terms of t, and so are dx and dy. So here so dx here, from here you can get dx is equal to x prime t dt, and from here you get replace dy with y prime t dt. So everything now would be in terms of t. Okay. Next is you have to get the lower and upper limit for t. So the lower limit would be the value of t at the initial point, so in this case t naught, and the upper limit for t would be the value of t at the destination point, which is tn, and then you integrate as usual. So for line integral of a vector field on a plane, you have three choices: either change everything in terms of x, or change everything in terms of y, or change everything in terms of t, depending on how the equation of your curve C is given. But if your curve is in x, y, z space, okay, you have no choice. There's only one choice, which is to change everything in terms of t. So here all the x, the y, the z in p and q and r, and also dx, dy, and dz, everything must be changed in terms of t. Okay, that's only one way of evaluating work in x, y, z space. Okay, for the examples, I'm going to leave that in our next video. Thank you.